All layouts can experience problems with their track work, but mostly at points with derailments and shorts and stalling. And what can we do to minimise these problems? That's the purpose of today's session. We're going to be looking at the optimum way to wire our points to avoid some of the problems, approaches to frog switching, and different methods to get feedback from the point to know that it has properly gone straight across and gone the full distance. Why are we looking at this? Because all points can be affected to one degree or another, and we can minimise problems with the way we wire up the elements of the point itself. And frog switching is an issue when we suffer stalling, not so much on very long, like diesels for example. I've got multiple wheels with pickups, but 040s and the smaller gauges, N gauge, 009 and so on, can suffer badly with short wheelbase locos, maybe only 17mm apart, be stalling at the frog. So how can we tackle that? And also, especially if you're going to be using automation, but not only that, you want to know that the point has fully moved across, maybe jammed with dust, dirt, pieces of ballast or whatever, mechanical problems, broken wire, whatever, and the point doesn't actually move at all or only partially moves and the blade doesn't fully go across. In the real world that's vital, and there are feedback methods on real railways, and if you want to do proper automation you want to know that when you throw a point that in fact has fully thrown. So that's the issues we want to look at. Starting with point wiring. So before we get into the hows, let's have a look at the nomenclature. What are the descriptions of the various parts of a point? As you can see, this is taken from British Railways themselves. So the main tracks are called the stock rails. The moving parts are called the switch rails. That's the parts that move to open and close the point. In model railways, they're usually attached, or almost always attached to the closure rails. There are also wing rails and check rails. The check rails are to make sure that the wheels go straight through with minimum problems. And then there's the V part here, which British Rail calls the crossing V, and commonly known to us as the frog. So when we're talking about it, these are the descriptions we'll be using. In model railways, apart from people who make their own points, there are two main types. These are showing pico points. The top two are called insel frogs for a reason. The frog part, as you'll see here, has a large component of plastic, both there and there. So there's an area when the local's coming across that the wheels don't make electrical contact before they make contact once again. And then there's electro frogs. used to describe the fact that there are no plastic. It's all metal all the way through, which gives you less chance of stalling, but has to be taken into account when wiring. Let's look at some of the problems with points. We're looking at one here which is very common in commercial points, where the two closure rails are bonded at production time. There's a metal link underneath the point that bonds the two of them together electrically. So these two closure rails are always at the same electrical potential. So in this example, the closure rails are to the top stock rail, and that means that the bottom closure rail is at a different potential from its neighbouring stock rail, which is fine if you're using fine scale wheels, because you're relying on the fact that the wheel can pass through here without shorting these two pieces together. But it's fairly common in locos to have wide wheels, in which case there's always the possibility when coming through to have a short at that point. How do we get round that? Well, we could break the link. If we take that link here away, then the closure rail here is at the same potential as the stock rail because it's touching physically here. The electrical contact here, but this blade is isolated, so there's no short when you go across. And the same, of course, when you throw the point the other direction, this closure rail now be electrically connected to the bottom stock rail, and that one will be unconnected. That kind of solves the problem there. But what happens if you have dirt here? A bit of ballast or a bit of grit or whatever, stops the rail from actually going across the blade, from actually touching the stock rail. In that situation, both closure rails and blades are disconnected effectively electrically, so it's going to stall. So we'd like to have some way that avoids shorts here, but doesn't rely on electrical contact here. Over a period of time you can get grime in between the blade and the stock rail, you can get corrosion or whatever, right, and get poor contact. So ideally we don't want to rely on the contact between the blade and the stock rail to provide electrical contact. Okay, how are we going to get around that? Well, we could do it that way. If you bond each closure rail to its appropriate stock rail, instead of having one link between both closure rails, we have a separate link between each closure rail and its associated stock rail. Now there's no possibility of shorts here, and there's no possibility of a poor contact here affecting performance. So far, so good, but we now have a problem here where the two rails are very close together, and that's why Pico brought out initial frogs. They effectively replaced this whole section here, as you can see, with a chunk of plastic. Removes the possibility of shorts at this point, but leaves you with a whole length where there's no metal track whatsoever, with all the problems or possibilities of stalling at the point. Insole frogs have benefits. Doesn't involve any special wiring to be done. It's fine as long as your locos have got long wheelbases, like diesels with multiple wheels with multiple pickups. But it's poor for locos with shorter wheelbases, 060s or 040s or N-gauge or 009 locos, where you only have possibly 2 wheels on each side with pickups. If one has a bad pickup, it means that when the good one arrives here, it's only getting powered from one rail and it stalls. And also, being plastic, it wears quicker than a metal component. Right, now we come to another possibility and solution, where we have these shorts at the wing rails. One way is to break where the short is most likely to happen. So you either cut it at that point, or even better, cut it further back so that that whole piece here has got no potential on it. We'll come back to that a bit later to overcome that, but that can solve the problem of shorts at this point here. You can use special tools for cutting the rail or a Dremel. And that leaves us lastly with shorts at the V crossing itself, because potentially we have the rails coming very, very close together at that point there. Even if we solve this point, we have a problem at this point. Over the years, people have come up with different solutions, putting a spot of paint on one of the rails, or a spot of paint on both of the rails. Of course, that solves the problem by causing another problem, because we've now got, once again, a chunk of rail that's insulated. And sometimes people put packing in the check rails, an extra piece of plastic glued on, for example, which is fine as long as your wheels are thin enough to go through. But if you've got wider wheels, it's going to jam there. So, possible solutions are there. But there are better solutions. And here's one of them. Pico's now introduced a unifrog range of points. There's one in O gauge. There's one in N gauge. And you see here, it's completely different in its construction. It's pre-cut here and pre-cut here. In some models they've put a plastic insert, in other models the metal comes all the way up. But what they've done is they've put bonding wires underneath, between here and here, between here and here, so that this rail and this rail are permanently at the same potential as is that one and that one. Because they've broken the connection here, these two are not connected together. You don't need to have plastic rail joiners here and here. You can just use ordinary metal rail joiners. It's also got links at this end between the blade and the stock rail. The closure rail here is permanently linked, as we discussed earlier. So it's done for us already. You don't have to put in links if you buy Unifrog. And then This piece here, you'll see a wire coming down. It's pre-wired to here for you. So when you take it straight out of the box, you don't have to put any connection to here if you don't want to. And then that piece would be dead electrically. In other words, it comes out the box as an insole frog. But because we have metal here, we can connect it up so it becomes an electro frog. With all the benefits I mentioned earlier, with older points, all being pre-done for you. You can just see there the break between this part of the frog and the stock rails. There's another change introduced by Pico in their Unifrog and some other models. You'll see in this one here we have the traditional setup where the closure rails and the blades have a pivot point. The closure rails are fixed and the blade's the moving part, and there's a kind of fish plate almost here that connects the two electrically and mechanically. Over a period of time that can become loose and a bit less reliable. So this other version of the Unifrog, you'll notice, has one continuous metal piece. In other words, the closure rail and the blade are one continuous piece. So it's not consistent across all of their models. You'll see that some have single blades, some don't. Some of the same type of rail code have pivots or no pivots. So to obtain the most reliable running through a point, it's preferable to have something like the Electro Frog equivalent, either because you've doctored your points, as we discussed a moment ago, or you've bought the Pico Unifrog. And that involves physically connecting the frog section, which is currently isolated, to one of the stock rails or the other, depending on which route you're going through the point. Let's look a bit further. If you're using Pico points, you can buy an accessory switch that's attached to the point motor itself. As the point motor moves, it operates a phosphor bronze switch. Something similar exists with the tortoise motors. They've got an internal switch, and you can see there that the frog section, which is isolated, will either connect to one stock rail or the other. So there's a switch internal here apart from the motor itself. I'm not a great fan of either of those two because they use phosphor bronze switches which can be corroded over time, giving bad contacts. Pico also produce this one for clipping onto the point motor, which they talk about as being microswitches, but again, that version you'll see the contacts are open to the elements. What you can do is put your own sealed microswitch such that it's operated by the tie bar. As the tie bar moves, it operates the microswitch, and then the frog can connect to the center and the two outers go to the two stock rails. So you can use switches to physically switch them. Another option are the frog juicers, which is essentially switching after you've found a problem. You detect a sudden increase in current is detected, and the frog juicer then will switch the frog to the appropriate stock rail. It's automatic, but it's very expensive for what it does, in my opinion. The Tam Valley frog juicers are for DCC only. They trip at 150 to 200 microseconds, so they switch over quicker before the short is detected by your DCC controller. Again, very simple. You connect the frog to the centre of a relay or an electronic circuit, which switches it to one stock rail or the other. Or we can simply use ordinary relays. In this case, we have a switch connected here that's going to operate, say, an Easy Points kit, or it's going to operate a Servo 4 module or whatever. So the same switch, which is going down to 0 to operate the servo, also connects to the relay. So the one switch does the manual operation and the electrical switching. And here is an example of the EasyBus output module. You'll see here Servo 5, when it operates, the I/O pin 5 also operates the relay at the same time. And your frog is here, and here are your two stock rails. So one operation does the mechanical movement and the frog switching at the same time. Pico do one called the Smart Frog. Again, expensive, it's only a relay and a couple of components. It's designed to be part of the larger Smart Switch setup. Again, not cheap, operates 4 servos and has outputs for LEDs to indicate which way it's switched. And all they do really is take those same ones that should go to LEDs and make them decide the switching of the frog. It's certainly not a cheap option. The Smart Switch set itself costs £82, and if you want to have frog switching for the 4 points that go with it, it's another £58. You're paying £140 to operate 4 points. On the other hand, in the Merg kit locker, you'll find the Servo 1 board, which will drive a servo and also has a relay for frog switching built onto the board for only £5.68. You buy the setting box once only, regardless of how many of these kits you want to operate with it. Now we're talking about quite close tolerances here. I checked the amount of movement in a tie bar for an end gauge point to be just 2 mil. So we have to accurately measure small amounts in either direction and take into account decompression. What I mean by that is if you use microswitches, then they are a sprung item. If you push a microswitch in, it wants to push back. And if you set up 2 microswitches, then we get double the pushback. And if you set your points to have removed the over-center spring, which you normally do with a servo, then there's a danger that it'll come across correctly, but it'll push back a little bit. So sometimes we don't want to use microswitches, we might prefer to use some non-contact method. And here are some we can look at. Here we have a reed switch at the side of the layout, probably under the ballast, and I put a neodymium magnet attached to the tie bar, and I checked it out, and the operating release is 2 mil. So it's a tight fit, but it would work with end gauge points. You get more latitude obviously with double O because the tie bar movement is greater, and greater again if you're up to O gauge. But it works, and it's a very simple way to do it. Or we can use Hall effect sensors. Pretty cheap, and they're tiny. So we're getting there, what, 10 for £2.34, 23 pence, it'd be 46 pence per point if you want to achieve feedback. The Hall effect sensor is very easy to connect to a PIC or an Arduino. As you can see there, it's only got 3 pins. 2 of them are power, and 1 is the output, which varies depending on the amount of magnetism it experiences. There are 2 kinds. This is a sensor, and what it's saying is that when there's no magnetism around, the output is at 2.5 volts. But if you bring a North Pole magnet close to it, the voltage will actually drop and continue dropping as the magnet gets closer and closer to the actual Hall effect sensor. If you put a South Pole magnet close to it, the voltage will increase as it gets closer and closer to the Hall effect switch. So we can read the output changes to let us know the magnet's position. Here's a short video clip showing exactly that same thing. Here we have an OH49E Hall effect switch. 5 volts across it, and the output taken to the voltmeter. I've got a neodymium magnet on the tie bar, and just watch the voltage change. Almost 4.5 volts. I move it about 1 mil and it's dropped to 3.5. Move it 2 mil and we've changed almost 1.5 volts. Very large swings for little tie bar movement. Or I can make the magnet go over and get a drop. So from 3 volts to 1 volt over about 2 mil. Well, that was the Hall effect sensor. As you noticed, the voltage varies with the magnetic field strength. There's another one that's called the Hall effect switch, because it acts like an on-off switch. It doesn't have a linear response. It either trips or doesn't trip, and it trips at a particular level. There's an example of them. Again, 28 pence, relatively cheap. There's part of its specification. Let's have a closer look. It says firstly that it's unipolar. In other words, it doesn't react to a north pole or a south pole. You can just use one magnetic field to operate it. It works over a fair range of voltages, so it can run off your 5 volt supply or your 12 volt supply. It can handle a fairly high current, up to 25 milliamps for just a small device. And it's got a Schmidt trigger. That's the circuitry inside that makes it either completely on or completely off, rather than linear. The Merck Kit Locker also sells this set of 5 Hall effect sensors. Different model, the DRV5033. But like the 3144 we looked at just a moment ago, it works in a switch mode. When the magnetic field comes to a certain level, it'll switch on. But like the 3144 before it, it has built-in hysteresis. What that simply means is, if it takes a certain amount to switch it on, when the magnetic field gets lower, it doesn't switch off at exactly the same point. Otherwise, if the magnetic field just happened to be hovering there with slight variations, it'd be switching on and off all the time. So hysteresis means it'll take a certain level to make it switch on, but it won't switch off until it's dropped below a certain level. So there's a gap between the switch on and the switch off, and that gap is called the hysteresis. So that could be used in place of the 3144 if you wished. Now we know we can use those kind of switches. We can mount them anywhere. We can mount them onto an Omega loop, for example, or under the baseboard, whatever is suitable to yourself. If you want even greater resolution, you can use the laser Totti kit, which has got a very narrow focus beam, therefore gives you great resolution. There's no wide beam. And if you replace the photo sensor with the PT333 that's supplied with the kit with a surface mount device, the PT1521C, it's absolutely tiny, 3.2mm by 1.5mm. And that means you can do things like this. We can have the tie bar here. We can mount the larger laser head under the layout, pointing up, and just across here we sight the photo detector. And the minute the tie bar comes across and breaks the beam, the photo detector spots it, and you know that it's got to that edge precisely. So we've looked at a range of detection devices. We've looked at reed switches and phosphor-bronze switches, microswitches, Hall effect switches, laser detectors, and so on. And they can be both used, as I said earlier, both for frog switching and for point feedback. There's no reason why you couldn't use a laser totty to detect the tie bar and switch the relay for frog switching, for example. But let's look in a little more detail at what could go wrong that you want feedback. What are the issues you have to look at? Well, the servo itself could become damaged, could be jammed inside, the gears sometimes slip. The motor could be burnt out for some reason. The horn that does the actual rotation may have got disconnected from the shaft. The link between the tie bar and the horn may have jumped out, the wire link or the omega loop. The tie bar itself might be impeded from moving because there's dirt between the blades. As we said earlier, a bit of ballast that stops the blades from coming fully across. Or there could be an electrical fault. The module that's driving the servo may have its power switched off, lost its power. There could be broken wires into the input of it. There could be broken wires between the module and the servo, and so on. There's a whole range of possible problems that you would have to detect, especially if you're going into automation. But not only that. If it's automation, then you could be using JMRI, Rockrail software to detect feedback from those points. But let's say you don't have a computer-based model railway, which is most of us. But you still want to know some critical points, say an exhibition or whatever, if anything happens to go wrong. How would we treat that? So we've covered quite a bit of ground today, and I wanted to leave you with a programming challenge. Let's have a look at this in more detail. We have the tie bar, we have a detector each end, as we said. We feed it into a PIC chip or an Arduino such that the input is going to operate the servo, and then check whether in fact it worked correctly. So if you've set the input switch to operate the point to main, and you get feedback from the main detector to say it's arrived there, all's well. If you switch the switch to make it point to branch, and you get feedback from the branch detector to tell you the tie bar's gone across correctly there, all's well. But how are we going to tackle all the other problems? Well, we can put a LED or a buzzer or whatever, or both, to indicate something's gone wrong. What are the possibilities? Here's a little chart we can look at. If you set the input to switch the point to main and you get feedback from the main, everything's okay. If you set it to branch and you get feedback from the branch detector, everything's okay. However, if it's been set to main and the branch detector is still indicating, then it hasn't switched at all. There's a fault. And similarly, if it's set to branch and you're still getting the main detector operating, it hasn't switched. If you set it to main or branch and neither detector are feeding back, it's stuck somewhere in the middle. The tie bar hasn't operated either of the detectors. So we've got various different kinds of fault detection. So the challenge would be, how would you write a little program as a little standalone module that would do that? We'd check for one point and check it did as it's meant to do. Or expand it to say, if you have a collection of points in the one local area on your layout, 4 or 5 points, then why not use a larger PIC or use a a nano or a uno to detect a group of points to make sure they're all working. If any one goes wrong, sound the alarm. And that, gents, is where we are. I'm sure we've all got lots of experience in points and their problems and how we tackle them, so I'm eager to hear other people's experiences. Are there any questions or comments or suggestions? Thank you.